Welcome back. So this is lecture 56 in this course on Bayesian modeling. The topic of today's lecture is Bayesian hierarchical models. Okay, this is actually last topic in this course, and this is the kind of models that we use for final hypothesis testing, and this is also in general very important kind of models because the simple model that we use, simple linear regression model, they violate some of the statistical assumptions that we make. So that's why it is important that we have these hierarchical models. Similarly, in frequentist framework, we have these linear mixed effect models. In Bayesian framework, we have these Bayesian hierarchical models. It's the same model, but it's just that in Bayesian framework, we write them as hierarchical models. All right, but let me explain why these models are required and how do we specify them. Okay, so consider this. Suppose you are recording marks scored by students from multiple schools. So let's say you are collecting data from 100 students. Okay, you are collecting data from 100 students. What kind of data? Marks scored by them in a subject, let's say mathematics. Okay, mathematics marks scored by 100 students. So you have 100 data points, and what you are recording, their marks in mathematics in a particular standard, let's say 10th standard. So how many marks they scored in mathematics in 10th standard, and you are collecting this data from 100 students. But all these students are not from a single school, they are coming from multiple schools. So let's say school 1, school 2, and so on, right? Such that from each school you have 10 students, right? So you have multiple schools. Let's say school 1, school 2, school 3, school 4, school 10, and from each school you have 10 students. The student 1, I will call it student 1 1. So first student from school 1, this is second student from school 1, this is third student from school 1, and this is 10th student from school 1. Similarly, you have 10 students from school 2. So student 2 1, student 2 2, student 2 3, student 2 10, right, and so on. So we have 10 students from each school. Okay, and what we are recording, their marks in mathematics, okay, scored by each student. Okay, now let us say we want to test this hypothesis that whether average marks in mathematics are greater than 70 or not. So let's say you have hypothesis 1, which says that the average marks in mathematics are greater than 70, and you have H naught, which says that average marks in maths are less than 70, less than or equal to 70. So two hypotheses, H1 which says that average marks in maths are greater than 70, H naught which says that average marks are less than equal to 70. Okay, how would you test them in the Bayesian framework? You will build model 1, which would say that marks scored by ith student comes from, or let's say ith student from jth school comes from normal mu sigma. Okay, so let's say these marks, this is our assumption that marks are normally distributed and they come from normal mu sigma, such that on mu you have a prior with lower bound of 70, because your assumption is that average marks of the students are greater than 70. So you assume that mu can have any value between, let's say, 70 and 100. Okay, so let's say upper bound is 100 and lower bound is 70, and this has some mean, let's say 70, and a standard deviation 10. This could be your model 1. What would be your model 2? Model 2 would be Yij marks scored by ith student from jth school comes from normal mu sigma, where mu comes from normal. Now here your upper bound is actually 70 and lower bound is, let's say, 0. Okay, and mean 70 and let's say ST is 10. So these are two different prior assumptions about mu in model 1 and model 2. So model 1 assumes that average marks are 70 and then individuals can differ, not in, basically average marks are 70, and we assume that this parameter mu can take any value between 70 and let's say 90. So the average marks are somewhere between 70 and 90. And model 2 assumes that the average marks are somewhere between 50 and 70, because here upper bound is 70. Okay, so that's the difference between model 1 and model 2. Okay, and then we can compare whether model 1 is better than model 2 given the data. Okay, this is fine. But there are two important assumptions that we are making here. Okay, and you have heard about these assumptions earlier. Assumptions are that the marks scored by students are assumed to be independent and identically distributed. What does independence means? That the marks scored by student 1 does not affect the marks scored by student 2. That's independence assumption, that all these marks scored by students are independent from each other. Second, marks scored by each student are coming from the same distribution, that marks scored by student 1 and marks scored by student 40, they all are coming from the same distribution. Okay, that's the assumption we are making here. So it doesn't matter who the student is and to which school the student belongs, their marks are coming from the same distribution, normal, mu, sigma. So that's our identical distribution assumption. And we also are making independence assumption, that marks scored by any student, let's say student 1, would not affect marks scored by student 2. Okay, so these are our assumptions, okay, about the kind of observations we will see in this experiment. But do these assumptions hold? It is always very important to ask that whatever likelihood assumption we are making, is this a reasonable assumption or not? We have questioned our assumptions previously, but in different context. So for example, when we were trying to model reaction times or reading times data, we challenged this assumption. So for example, some models make this assumption that reaction time in ith trial comes from normal mu sigma. We challenged this assumption because the actual reading times that are observed in human studies, they are not normally distributed. So that's why we challenged this assumption and we changed this assumption to this, that reaction times in ith trial comes from log normal distribution, log normal mu sigma rather than normal mu sigma. Okay, this was a better likelihood assumption. This was a poor likelihood assumption. So we always want to specify a better, a more reasonable likelihood assumption. Okay, so your likelihood, so generative process that we are defining or that we are assuming should be such that it mimics the properties of your observed data. Okay, we do not want to make an assumption which deviates from kind of data that we see. So we always want to be more reasonable and closer to our observed data in our likelihood assumption. Okay, so the likelihood assumption we are making here, it is fine. Marks are typically normally distributed, so this part is fine. But there is another set of assumptions we are making here, which is that marks scored by each student are independent and identically distributed. Now this assumption can be challenged here. Why? Because remember how these data were generated. You have data from 100 students, but these are not 100 students from the same school. These students are coming from different schools. So 10 students are coming from school 1, 10 students are coming from school 2, and so on. Would they still satisfy the independence and identically distributed assumption? The answer is no, because schools can differ in terms of their teaching style, quality of teachers, how much practice students do, school culture. There could be so many things that can differ across schools, and that would affect what marks do students score in these schools. So, for example, let's say these students from school 1 score high marks, then it is very likely that other remaining students from this school also score high marks. That could be just because this school is really good compared to school 2. Similarly, it can happen that these students from school 2 score low marks. It could be the case that other students from this school would also score low marks. Okay. So, all these school level data points are correlated. Okay. So, this violates the independence assumption. Now, you cannot claim anymore that all these observations are independent of each other, because there are clusters in this data. Okay. So, the data looks actually something like this. If, let's say, I want to show marks scored by these 100 students, let's say x axis shows marks scored by each student. Okay. And let's say they are like this. So actually, there are some clusters in this data. And clusters are such that, so let's say these are 2, 3 bad schools, and these are, let's say, good schools. Okay. So there are clusters of this sort. Okay. This is more easily visualizable in this sense that, let's say, this is a school 1, this is a school 2, this is a school 3. Okay. So let's say the school 1's scores are like this, school 2 scores are like this, school 3 scores are, let's say, like this. Okay. They are not at same level, there could be differences, right? But importantly, the point to consider is that these observations, the student level scores, are not independent from each other, because marks of the students who belong to same school, they are highly correlated. Okay. So they could be, they all are high or they all are low, depending on the quality of the school, right? So we cannot make this claim that these observations are independent from each other. There are clusters, there is structure in this data, right? There is hierarchical structure in this data. Okay. Second, can we say that all these marks are identically distributed? We also cannot make this assumption. We cannot really say that these marks scored by all the students will be identically distributed. Would they come from same distribution? Maybe not. It could be the case that average marks of school 1 students are higher than average marks of school 2 students, and that would violate the identically distributed assumption. So, in fact, you can write a more reasonable assumption about these kind of scores would be this, that marks scored by ith student from jth school comes from normal mu j sigma. What does it mean? That marks scored by ith student from jth school comes from a normal distribution with school level mean. This is a school level mean score mu j. So average marks scored by school j. Okay. And this is sigma, overall population level sigma, right? Now mu j school level mean marks, let's say, also comes from normal mu tau, where this mu is actually average marks of whole student population. This is the same mu that we had in our previous models. So, average marks of whole student population. This is differences in schools. So, differences across schools. So, how different are schools from each other in their average marks? Okay. So, basically school level average marks comes from this distribution normal mu tau. Okay. So, you can call it school level differences in average marks, right? Okay. This is alternative likelihood assumption about the same data, that marks scored by ith student from jth school comes from normal mu j sigma, where mu j is school level average. Okay. Mu j is school level average marks, or let me write it like this: average marks of school j students. Okay. Where mu j comes from normal mu tau, where mu and tau are population level parameters, and this mu j is a school level parameter or group level parameter. Now, this is a better likelihood assumption, because if we see the structure of the data, how this data was generated, it makes sense to assume this, because what this model implies is this, that there is some population level mu which indicates average competence of the student population, let's say entire student population of India. So, this mu indicates average marks scored by entire student population of India. Okay. So, you can call this population level average. Now, conditional on this population average, you have school level averages. So, school level competence. So, competence of school 1, school 2, school 3, school 4, and let us say school n. Okay. What do you have for all these schools? School level mu. So, let us call it mu 1, mu 2, mu 3, mu 4, mu n. Okay. How these mu's are being generated? They actually come from normal mu tau, where tau is school level differences, mu is population level mean. So, average marks scored by entire student population of India, mu 1, mu 2, mu 3, mu 4, mu n are basically competence for school J. Okay, so, they are indicating average marks scored by student in school J, in school 1, school 2, school 3, like that. Okay. Now, from here, the process is generating student level scores. So, let us say this is a score, this is the score by first student from school 1, this is second student from school 1, this is third student from school 1, this is nth student from school 1, nth, or let us say capital J. Similarly, here this is score by first student from school 2, this is second student from school 2, this is third student from school 2, this is nth, jth student from school 2, and so on. So, this is the hierarchical structure. That is what the model assumes. That is why these are called hierarchical models, that there is some population level mu that generates school level mu's, school level average scores, and from school level scores you get student level scores. Okay. That is why this is hierarchical model. That is why these are called hierarchical model. Okay. And this is the exactly the kind of a structure we have in our data. So, this is this model, these model assumptions are closer to the actual data that we see, because marks scored by students from a single school will be closer to each other. Okay. They will be highly correlated, and because they are coming from same generative process, normal mu 1 sigma. So, all these are coming from normal mu 1 sigma. Similarly, marks scored by school 2 students are coming from normal mu 2 sigma. So, they are not identically distributed, they are coming from different distributions. But within a single school, these data points, they follow an IDD assumption. Okay. So, scores by students from a single school, they follow the IID assumption. They are independent as well as identically distributed. But overall, all these observations, you cannot say that they are independent identically distributed. About all the observations, you can make a different kind of claim or different, basically a weaker version of this IID assumption. These observations are called exchangeable. So, although they do not follow IID assumption, they follow the exchangeability assumption. What is exchangeability assumption? Exchangeability assumption is this, that the joint probability, okay, so joint probability distribution of, let us say, these school level scores, okay, the joint probability distribution of them would remain the same even if you change their sequence. Okay. So, for example, the joint probability of mu1, mu2, mu3 and mu1 would remain the same even if you change their permutation. So, let us say you write mu3, mu2, mu1 and mu n. Okay. Similarly, the joint probability distribution of y11, y11, y12, y13, y1n would remain the same even if you change their order, their permutation 13, p12, p11 and so on. Okay. In fact, you can also say that this is just property of exchangeable random variables, that they are conditionally independent and identically distributed. That under the assumption, so for example, if I think about these data points coming from school 1, y11 to y1n, okay. So, you can say that these are independent and identically distributed conditional on if mu1 comes from normal mu sigma. Basically conditional on this mu1 which comes from normal mu sigma. Okay. So, all exchangeable random variables will follow conditional independent identically distributed assumption. Okay. So, this is a conditional assumption being followed. So, this exchangeability is actually a weaker version of independent and identically distributed assumption, okay, which says that joint probability distribution wouldn't change even if you change the sequence of the random variables. Okay. But the main point that we are concerned about here is that if you have data of this sort, let us say there are multiple groups in your data, and that can happen in human studies a lot. So, let us say you are doing a word recognition experiment on 5 subjects. Okay, there are 5 subjects who are going to do this task where they have to recognize whether it is a proper word of English or it's a meaningless string in English. Okay, so whether it's a word or non-word. So, word recognition study, and you recruited 5 subjects who are going to do this word recognition study. So, let us say this is subject 1, this is subject 2, okay, this is subject 3, this is subject 4 and this is subject 5. Okay. And let us say for each subject you test on 100 words, right. You show 100 strings or words to each subject and you record their recognition times. And let us say these are the recognition times by each subject on 100 trials. So, this is recognition time on first word by first subject, RT11. This is RT12, recognition time by first subject on second word. This is RT13. How much time does subject 1 takes to read word number 3? This is RT1n. Similarly, here you would have RT21, RT22, RT23, RT2n and so on. Okay. So each subject is reading 100 words and we are recording their reaction times on each word. Okay, so this data already has some hierarchical structure. So similar to our school marks example, this would also violate the IID assumption if we would try to assume that RTIJ, reaction time on ith word by jth subject, comes from normal mu sigma. This is the assumption we have been making so far in our linear regression models, right? What we do in linear regression models, that RTIJ comes from normal mu I sigma such that mu I equals to alpha plus beta into condition, or let's say frequency. Let's say these average reaction times are affected by frequency. So frequency I, frequency of the ith word. This assumption can change, let's say log normal. This is what we have been doing so far in our linear regression models. Okay, that reaction time for the ith word depends on mu I, where mu I is alpha plus beta into frequency I. But this is not a very good likelihood assumption, because this is not how this data is being generated, because subjects can differ. Subjects can differ in 2-3 ways. One, subjects can differ in their average processing speed. So some subjects can be faster than the others. Second, subjects can differ in how sensitive they are to the frequency of the words. So some subjects may have more language experience than others. So some subjects show a stronger effect of frequency, some subjects might show weaker effect of frequency. So subjects can systematically differ from each other. And what would that do to our data? It would violate independence and identical distributed assumption, because now the scores, basically the reaction times from an individual subject, will be correlated. So if let's say these 2-3 reaction times from subject 1 are high, it is likely that other reaction times are also high. Okay, so this violates the independence assumption, that all these reading times or reaction times across subjects, these are not independent anymore, because they are clusters, they are coming from different subjects. So subjects from a single individual subject will be correlated with each other. Second, they may also violate identically distributed assumption, because it could be the case that individual subjects have different processing speeds. So different value of alpha, which indicates average speed, which indicates average recognition time for any subject, and beta indicates how much is the effect of frequency. So how sensitive is someone to frequency. So subjects can differ in alpha and beta. So that would violate the independence of the identically distributed assumption, right? So this likelihood assumption is basically not reasonably good enough, right? So this is not a reasonable assumption. We need to change this. So how do we change this likelihood assumption so that it is closer to the way the data was actually generated, so that it follows the exchangeability assumption and it does not, let's say, it does not violate the way data was generated. Okay, so what we can do here is this, that recognition time for ith word from jth subject comes from log normal mu ij. So rather than coming from mu I, it comes from mu ij, such that this average recognition time can differ across items, across words, as well as across subjects, and sigma, where mu ij can be written as alpha j plus beta j into frequency I. Okay, so mu ij would be determined by alpha j, beta j into frequency I. Alpha j means that the subjects can have different processing speed. So alpha interpretation of alpha j is like this: when the value of frequency is 0, alpha j indicates the average recognition speed. Beta j is effect of frequency, to what extent frequency affects recognition times. Individual subjects can differ in both alpha and beta. So individual subjects can differ in their average recognition times, basically in their processing speed, they can also differ in how sensitive they are to frequency. So we can further write that, let's say alpha j comes from normal alpha tau 1 and beta j comes from normal beta tau 2. These are our assumptions about how individual level processing speeds and individual level frequency effects are distributed. We are assuming that they come from normal distribution with population level beta and population level tau. When we test our hypothesis, this is usually the parameter of interest for us, the population level effect of frequency, right? But we need to specify our likelihood assumption in this way. Although the main parameter of interest for us is this beta, population level beta, but we still need to specify the model this way, because this is a more reasonable, more correct likelihood assumption given the data. Okay. All right, I will stop here. So this is the basic intro and motivation for why do we need hierarchical models. In the next lecture, we will talk more about how we can specify different types of hierarchical models, right? And how these hierarchical models can encode our assumptions about how individuals are distributed in the population, that how individuals differ from each other. We can actually use these models to model individual differences on a certain measure in the population, right? All right, I will stop here, and in the next lecture, we will talk more about hierarchical models and individual differences. All right, thank you.